July 3, 1938, Stoke Bank, Lincolnshire. The sleek Azure locomotive waiting at Barkston Junction defied every principle that British railway engineers had established about steam power limitations. A streamlined shell encasing 165 tons of steel, brass, and ambition. LNER, Class A4 number 4468. Christened Mallard, prepared for a test run that most experts predicted would end in catastrophic mechanical failure through the morning mist along the East Coast Main Line. Locomotive designers watched with professional skepticism. Steam engines, they insisted, faced absolute physical barriers that no amount of engineering creativity could overcome. Track stress, wheel balance, boiler capacity, each presented hard limits that decades of railway experience had proven immutable. By 1938, steam locomotive technology had reached what continental engineers called thermal and mechanical equilibrium. The fastest regular services operated around 90 miles per hour. Speeds achieved through incremental improvements over 50 years of development. European railway theory held that pushing beyond 120 miles per hour courted disaster. Driving wheels would lose contact with rails. Axle bearings would seize from friction heat. And boiler pressures would fluctuate dangerously. Germany's DRG Class 05 had touched 124.5 miles per hour in 1936. But German engineers emphasized this represented steam's absolute ceiling. Their calculations showed that aerodynamic drag increased exponentially beyond 115 miles per hour, requiring boiler outputs that standard firebox designs couldn't sustain. The mathematics were clear. Steam locomotives lacked the power-to-weight ratios necessary for sustained high-speed operation. British railway establishment figures shared this continental pessimism. The Great Western Railway's engineers argued publicly that chasing speed records diverted resources from practical improvements that actually benefited passenger service. Why risk expensive locomotives and valuable track pursuing speeds that regular services would never utilize? Their position reflected decades of conservative engineering philosophy that prioritized reliability over performance records. Sir Nigel Gresley, chief mechanical engineer of the London and North Eastern Railway, faced institutional resistance that went beyond technical skepticism. His streamlined A4 class locomotives, introduced in 1935, generated controversy from their first public appearance. Critics dismissed the aerodynamic casings as publicity stunts, expensive sheet metal that added weight without delivering measurable performance benefits. Railway engineers trained in traditional locomotive design viewed Gresley's streamlining with professional disdain. Steam locomotives weren't aircraft, they argued. At railway speeds, aerodynamic considerations mattered far less than proven mechanical principles: cylinder efficiency, valve timing, and boiler steam production. The streamlined casing that made Mallard visually distinctive represented to critics engineering resources wasted on aesthetics rather than functionality. The technical arguments against high-speed steam operation carried legitimate weight based on operational experience. Every component in a steam locomotive endured extreme mechanical stress. Driving wheels spinning at high velocity generated centrifugal forces that could crack castings or throw balance weights. Connecting rods reciprocating hundreds of times per minute experienced metal fatigue that led to catastrophic failures. Boiler tubes conducting superheated steam developed stress cracks under thermal cycling. Most damning was the power limitation inherent in steam technology. Unlike internal combustion engines that could increase power output through higher RPMs, steam locomotives depended entirely on boiler steam production. Fireboxes had fixed volumes, limiting fuel combustion rates. Water circulation systems could only transfer so much heat before encountering physical limits of thermal conductivity. These weren't engineering challenges, they were laws of thermodynamics. The morning Mallard prepared for its record attempt. Conventional wisdom held that Gresly was pursuing an impossible goal that would likely damage an expensive locomotive without advancing practical railway technology. The debate over streamlining exposed fundamental divisions within British locomotive engineering. Traditional designers had spent careers perfecting steam locomotives through incremental improvements to established principles. Gresly's approach, encasing a locomotive in aerodynamic bodywork, struck them as continental excess imported from aircraft design. Irrelevant to railway engineering realities, William Stanier, chief mechanical engineer of the London Midland and Scottish Railway, represented the establishment. His locomotives achieved excellent performance through refined conventional design, efficient boilers, precisely timed valve gear, and careful attention to mechanical details. Stanier's philosophy held that locomotive performance came from internal machinery, not external appearance. Adding streamlined casings, he suggested, was like putting a racing body on a cart horse. The engineering calculations seemed to support traditional skepticism. At 60 miles per hour, aerodynamic drag accounted for only about 15% of total locomotive resistance. Rail friction, mechanical resistance in the motion, and the energy required to accelerate the train's mass dominated the power equation. Spending design resources and manufacturing costs on streamlined shells appeared to address a minor factor while ignoring major ones: wind tunnel testing. Still primitive in the 1930s, provided ambiguous results. Some tests suggested streamlining reduced air resistance at high speeds, but the magnitude of benefits remained unclear. Critics pointed out that steam locomotives operated in constantly varying conditions, crosswinds, tunnel entrances, passing trains that negated any theoretical aerodynamic advantages, calculated in controlled laboratory environments. The practical objections extended beyond performance questions. Streamlined casings complicated maintenance access to critical components. Mechanics needed to remove sections of bodywork to reach valve gear, driving axles, and lubrication points. This added time and labor costs to routine inspections that traditional locomotives allowed mechanics to perform quickly. Railway workshop managers calculated that streamlined locomotives required 30% more maintenance hours for equivalent mileage. Weight considerations troubled conservative engineers. Mallard's streamlined casing added approximately 2 tons of steel and aluminum to the locomotive's mass weight that contributed nothing to pulling power. Those 2 tons could have been invested in larger boiler capacity or stronger frames. Improvements that directly enhanced locomotive capability rather than merely improving appearance. Gresly's continental influences made establishment engineers suspicious. He had studied aerodynamics research from Germany and France, where railway engineers embraced streamlining more enthusiastically than their British counterparts. The Deutsche Reichsbahn had introduced streamlined locomotives in the early 1930s, but British engineers viewed these as publicity exercises, designed to project modernity, rather than serious technical improvements. Aesthetic aspects of streamlining particularly annoyed traditional designers. Railway engineering was about function, not fashion. Locomotives were working machines that moved freight and passengers, not sculpture to be admired. The curved casings and Art Deco styling of A4 locomotives suggested that Gresly cared more about visual impact than engineering substance. Financial pressures intensified the controversy. The LNER operated under constant budget constraints throughout the 1930s. Every pound spent on streamlined bodywork was a pound unavailable for track improvements, signaling upgrades, or additional rolling stock. Board members questioned whether Gresly's design choices served railway operational needs or his personal ambition to create visually impressive locomotives. Yet, Gresly possessed operational data that undermined traditional objections. A4 locomotives in regular service consistently outperformed conventional designs on identical routes. They maintained schedules with less coal consumption and delivered smoother rides that passengers noticed. Something about the streamlined design was working, even if establishment engineers refused to acknowledge it. Controversy revealed that technical debates often masked deeper conflicts about engineering philosophy and professional status. Mathematical barriers facing high-speed steam operation went far beyond aerodynamics. Every aspect of locomotive design encountered physical limits that seemed absolute. Understanding why engineers considered 120 miles per hour impossible requires examining the brutal mechanical realities of steam power at extreme speeds. Reciprocating mass presented the most fundamental problem. Steam locomotive driving wheels connected to pistons through connecting rods that moved back and forth hundreds of times per minute. At 126 miles per hour, Mallard's driving wheels would rotate 527 times per minute. The connecting rods, each weighing several hundred pounds, had to reverse direction twice per revolution, creating enormous inertial forces that stressed every component. The energy required to accelerate and decelerate this reciprocating mass increased with the square velocity. Double the speed, quadruple the forces. At very high speeds, more power went into moving the locomotive's own machinery than into pulling the train. Engineers calculated that beyond certain velocities, additional boiler power produced diminishing returns because mechanical losses consumed the extra energy. Wheel balance became critical at high speeds. Even microscopic imbalances in driving wheels created vibrations that amplified dramatically as rotation speeds increased. A wheel imbalance of 1 ounce at 50 miles per hour became a 100-pound hammering force at 125 miles per hour. These vibrations could crack wheel centers, fracture frames, or cause wheels to momentarily lift off rails, any of which meant certain derailment. Dynamic augment. The vertical forces that driving wheels exerted on track increased exponentially with speed. Locomotive wheels didn't roll smoothly. They pounded rails rhythmically as connecting rods drove them forward. At high speeds, this pounding delivered impact forces that could break rails, shatter ballast, or damage track foundations. Railway civil engineers established speed limits based on track strength as much as locomotive capability. Boiler steam production faced thermodynamic constraints that seemed insurmountable. Fireboxes could only burn coal at certain rates determined by grate area and airflow through the firebox. Water circulation through boiler tubes depended on convection currents that had maximum flow rates. Increasing train speed required proportionally more power, but boiler output couldn't increase indefinitely. The specific problem involved steam flow through cylinders. At higher speeds, cylinders needed steam faster than boiler tubes could deliver it. Pressure dropped in the steam passages, reducing the power each piston stroke produced. Engineers called this steam starvation, cylinders gasping for steam that the boiler couldn't supply quickly enough. This created a practical speed ceiling independent of any other consideration. Valve gear timing presented another limitation. Steam admission valves had to open and close precisely to maximize cylinder efficiency. At low speeds, valve timing could be optimized for power. At high speeds, the same valve settings became inefficient because steam didn't have time to enter and exhaust properly. Designing valve gear that worked efficiently across wide speed ranges proved extraordinarily difficult. Bearing temperatures skyrocketed at high speeds. Axle bearings supporting 20 tons while rotating hundreds of times per minute generated tremendous friction heat. Lubrication systems struggled to maintain oil films between metal surfaces. Bearing failure at high speed meant instant derailment with catastrophic consequences. British engineers reviewing these physical constraints concluded that 120 miles per hour represented steam's practical limit. Exceeding it wasn't merely difficult, it defied mechanical possibility. Yet Gressley believed that systematic engineering could overcome what others considered absolute barriers. If approached with sufficient rigor and innovation, Gressley's approach to breaking the speed barrier demonstrated how methodical innovation could challenge established limitations. Rather than accepting that steam locomotives faced insurmountable physical constraints, he systematically addressed each technical barrier through design, solutions that traditional engineers hadn't considered necessary or practical. The streamlined casing wasn't cosmetic, it was precisely calculated aerodynamic engineering. Wind tunnel testing at the National Physical Laboratory provided data showing that carefully shaped bodywork reduced air resistance by 35%, above 90 miles per hour compared to conventional locomotive profiles. Gressley's design team spent months refining the nose shape, boiler casing curves, and cab contours to minimize turbulence and reduce drag forces. The aerodynamic benefits became substantial at extreme speeds. At 126 miles per hour, air resistance accounted for nearly 60% of total locomotive resistance. The streamlined shell reduced the power required to overcome air drag by approximately 1,200 horsepower compared to an equivalent conventional locomotive. This wasn't marginal, it was the difference between possible and impossible. Boiler design received revolutionary attention. Mallard's boiler operated at 250 pounds per square inch, higher than most contemporary locomotives. But pressure alone didn't solve the steam production challenge. Gressley's team enlarged the firebox grate area, optimized water circulation through the boiler tubes, and carefully calculated tube diameters to maximize heat transfer from combustion gases to water. The critical innovation was the Killchap double exhaust system. Designed by Finnish engineer Kesti Kilcoke and refined by French engineer André Chapelin. This sophisticated exhaust arrangement used two blast pipes instead of one, creating more efficient draft through the firebox while reducing back pressure in the cylinders. The system allowed the boiler to burn coal more completely and deliver steam to cylinders with less restriction. Traditional single blast pipes created strong draft but caused excessive back pressure that fought against pistons during exhaust strokes. The double exhaust balanced draft strength with minimal cylinder resistance, effectively giving Mallard additional power without increasing boiler size or pressure. This represented the kind of systematic efficiency improvement that multiplied small gains into substantial performance advantages. Wheel balancing received unprecedented attention. Each driving wheel was dynamically balanced to tolerances measured in fractions of ounces. The connecting rods were precisely weighted and balanced to minimize the reciprocating forces that stressed the machinery. Gressley understood that at extreme speeds, minor imbalances would amplify into destructive vibrations. So every rotating and reciprocating component received meticulous balancing treatment. The valve gear used Gressley's own patented conjugated design, which operated the center cylinder's valves through a linkage connected to the outside cylinder's valve gear. This mechanically complex system maintained efficient valve timing across wide speed ranges, ensuring cylinders received proper steam admission even as locomotive speed varied dramatically. The precise mechanical coordination this required represented machine tool manufacturing at its finest. Metallurgy played a crucial role that traditional designers underestimated. Mallard's connecting rods, crank pins, and axles used specially selected steel alloys chosen for high tensile strength and fatigue resistance. Every component that would experience high stress cycles was manufactured to specifications that exceeded standard railway practice. Gressley treated locomotive construction more like aircraft engineering than traditional railway machinery building. The chassis frame incorporated subtle flexibility, carefully calculated to absorb dynamic forces while maintaining structural integrity. Completely rigid frames transmitted every track irregularity as harsh vibrations. Gressley's design allowed controlled flexing that damped oscillations and reduced the hammering forces that damaged both locomotive and track.